Welcome to one of the most embarrassing problems in physics, the vacuum catastrophe. This is the vacuum catastrophe. Quantum theory predicts a value 10 to the 113 times larger than what we observe. This is the worst prediction in the history of physics. Let's start by understanding what vacuum energy actually is. The first surprising fact: empty space is not actually empty. Even in a perfect vacuum, quantum physics tells us something remarkable is happening. Virtual particle pairs constantly pop in and out of existence. Particles and antiparticles appear, exist briefly, then annihilate. This happens everywhere, all the time. The Heisenberg uncertainty principle allows these particles to borrow energy from nothing, as long as they pay it back quickly enough. This is expressed mathematically as delta E times delta T is greater than or equal to h bar over 2. The more energy borrowed, the faster it must be returned. Now let's see how quantum field theory calculates the vacuum energy density. In quantum field theory, every possible mode of vibration in every quantum field contributes energy. Even the lowest energy state, the ground state, has non-zero energy. The zero-point energy for each mode is 1/2 h bar omega, where omega is the frequency of oscillation. To get the total vacuum energy, we need to sum contributions from all possible frequencies, up to the Planck scale, where our physics breaks down. The vacuum energy density is 1/2 times the integral from 0 to Planck frequency of omega times the density of states. The Planck scale is where quantum gravity effects become important, and our current physics breaks down. The Planck length is the square root of h bar g over c cubed, which equals approximately 1.6 times 10 to the minus 35 meters. Energy contributions grow with frequency. We cut off at the Planck scale because we don't know what happens beyond that. When we perform this calculation, we get an enormous number. The predicted vacuum energy density is approximately c to the 7th power divided by h bar g squared. Numerically, this gives us about 10 to the 113 joules per cubic meter. This is an unimaginably huge number. Let's put this in perspective. What does 10 to the 113 joules per cubic meter actually mean? 1 cubic meter of empty space should contain enough energy to power the entire universe for longer than its current age, many times over. Now let's look at what we actually observe. In 1998, astronomers discovered that the universe's expansion is accelerating. This acceleration is caused by dark energy, which behaves exactly like vacuum energy. The observed dark energy density is approximately 10 to the minus 9 joules per cubic meter. This is incredibly tiny. The universe is expanding, and dark energy is pushing galaxies apart faster and faster. But the amount of energy needed is minuscule compared to predictions. Let's compare these two numbers directly. The ratio is 10 to the 113 divided by 10 to the minus 9, which equals 10 to the 122. Our prediction is off by 122 orders of magnitude. This is the worst theoretical prediction ever made in physics. It's not just wrong, it's spectacularly catastrophically wrong. If the prediction were a bar 4 meters wide, the observation would be thinner than an atom. The scales are incomprehensibly different. Let's use an analogy to understand how absurd this discrepancy is. Imagine you carefully track every deposit and withdrawal in your bank account. You calculate you should have a certain amount. You expect $10 trillion based on your calculations. But when you check, you only have $100. Where did $10 trillion go? This is exactly what's happening with vacuum energy. Our theory says there should be an enormous amount, but we only observe a tiny amount. Something must be canceling out almost all the predicted vacuum energy. But we have no idea what that something is or why the cancellation is so precise. Why should we care about this problem? What makes it so important? If the quantum field theory prediction were correct, the universe would have been torn apart instantly. Space would expand so fast that atoms couldn't form. The enormous vacuum energy would cause catastrophic expansion, making the universe uninhabitable within fractions of a second. The fact that we exist proves that either our calculation is wrong, or there's a profound mechanism we don't understand that cancels this energy. Physicists have proposed several solutions to the vacuum catastrophe, but none are fully satisfactory. Supersymmetry proposes that every particle has a superpartner. The contributions from particles and superpartners could cancel out. In supersymmetry, particles contribute positive energy, and superpartners contribute negative energy. Perfect symmetry would give exact cancellation. The problem is that no superpartner particles have been found at the Large Hadron Collider, despite extensive searches. Another approach is the anthropic principle, which takes a very different perspective. The anthropic principle suggests that many universes exist, each with different values of vacuum energy. Most are uninhabitable. We find ourselves in one of the rare universes where vacuum energy is small enough for life to exist. We couldn't observe any other universe. The problem with this explanation is that it's not really testable or predictive. It doesn't explain why the value is what it is. Let's understand why such extreme fine-tuning is needed. The total vacuum energy density equals quantum contributions plus the cosmological constant term. For the observed value, these two enormous numbers must cancel each other out to 122 decimal places. This is like balancing on a knife edge thinner than an atom. The cancellation must be precise to 1 part in 10 to the 122. This is far beyond any known physical mechanism for fine-tuning. The vacuum catastrophe is intimately connected to dark energy, the mysterious force accelerating cosmic expansion. Dark energy makes up 68% of the total energy content of the universe. It dominates over both matter and dark matter. Here's the energy budget of the universe. Dark energy dominates. Dark matter is 27%. Normal matter, everything we can see, is just 5%. Vacuum energy is the leading theoretical explanation for dark energy. But we can't explain why it has the tiny value we observe. Let's look at Einstein's cosmological constant and its role in this puzzle. Einstein's field equations with the cosmological constant lambda. Lambda represents the energy density of empty space. Einstein added the cosmological constant to make the universe static, then removed it, calling it his biggest blunder. Now we know it's needed, but we can't calculate its value. The observed cosmological constant is about 10 to the minus 52 per meter squared. This is extraordinarily small. Every particle that exists contributes to vacuum energy through quantum corrections. Every type of particle we know contributes to vacuum energy. Electrons, quarks, photons, neutrinos, all of them add their quantum fluctuations. All these particles create a sea of quantum fluctuations. Each one adds energy to the vacuum. The sum should be enormous. Every time we discover a new particle, it makes the vacuum catastrophe worse. More particles mean more quantum corrections, driving the predicted value even higher. A natural question. Why can't we just declare that vacuum energy is exactly zero? We can't set it to zero because we observe its effects. The universe's accelerating expansion proves dark energy exists. Galaxy clusters are moving apart faster and faster. This acceleration requires a positive, non-zero vacuum energy density. The Casimir effect provides direct experimental evidence that vacuum energy is real. Two metal plates in vacuum experience an attractive force from quantum fluctuations. Let's put the scale of this problem in more concrete terms. Imagine if you could weigh the predicted vacuum energy versus the observed amount. The prediction would weigh as much as all matter in the observable universe. The observation would weigh as much as a single atom. The ratio is that extreme. This is worse than finding a specific needle in all the haystacks that have ever existed on Earth. It's precision beyond anything else in physics. What does this catastrophe tell us about fundamental physics? Either quantum field theory, our most successful theory ever, has a fundamental flaw we haven't discovered, or general relativity, our theory of gravity and space-time, breaks down in some subtle way we don't understand. Or there's completely unknown physics, perhaps at energies we can't reach, that cancels vacuum energy through a mechanism we haven't imagined. The overlap region between quantum field theory and general relativity is where the problem lies. Something fundamental is missing from our understanding. With all our theoretical tools, why haven't we solved the vacuum catastrophe? The problem spans from the Planck scale, the highest energy we know, down to cosmological scales, the largest distances in the universe. Solving it likely requires unifying quantum mechanics and gravity, which is the holy grail of theoretical physics that has eluded us for a century. We have no consistent theory that bridges quantum mechanics and gravity. The vacuum catastrophe lives right in this gap. What would a solution to the vacuum catastrophe actually look like? A solution must explain the precise mechanism that cancels quantum vacuum energy down to the tiny observed value. It must be testable and make predictions we can verify. The anthropic principle fails this test. It will likely require discovering a new symmetry in nature or entirely new physics beyond our current standard model. Mathematically, we need some new physics contribution that makes this equation work. Quantum plus new physics plus cosmological equals the observed tiny value. What are physicists currently working on to solve this problem? String theory attempts to provide a framework where vacuum energy might naturally be small through geometric properties of extra dimensions. Some physicists explore modifications to general relativity that change how vacuum energy gravitates. Asymptotic safety proposes that quantum gravity becomes well-behaved at high energies in a way that naturally suppresses vacuum energy. Multiple research programs are attacking the problem from different angles. So far, none have succeeded completely. Let's summarize what makes the vacuum catastrophe so profound. It's the worst prediction in all of physics, wrong by 122 orders of magnitude. No other theory has ever been this far off. It reveals a fundamental gap in our understanding between quantum mechanics and gravity. Solving it will require revolutionary new physics, possibly more radical than relativity or quantum mechanics were in their time. The vacuum catastrophe stands as the biggest mystery in fundamental physics, a 122 order of magnitude question mark at the heart of our understanding of reality. Our existence depends on this mysterious cancellation. If vacuum energy were much larger, the universe would have torn itself apart. If it were much smaller or negative, the universe might have collapsed. When we finally solve the vacuum catastrophe, the answer will likely reshape our entire understanding of space, time, and the quantum world.